In this lesson, we're going to compare intramolecular forces versus intermolecular forces. So we'll start by looking at intramolecular forces, and the first thing to look at is that prefix, intra. The prefix of intra means within. So if we look at that word, that says intramolecular, that just means within the molecule. So what are the forces that are within the molecule? Well, those would be forces that keep the compound together. So those are the forces between atoms or ions. These are your chemical bonds. And if you break these bonds, so breaking these bonds in molecular substances results in a chemical reaction. Okay, just to recap those 3 points, the first type of forces that we're looking at are called intramolecular forces. So these are the forces within compounds, and so they could be forces holding atoms together within a compound or ions together. And then you have chemical bonds, which is just another way of saying intramolecular forces. And if you have molecular substances and you break these chemical bonds, then you end up with a chemical reaction because the chemical bonds will rearrange and you'll form new compounds. So in molecular substances, there are 2 forces that hold the atoms together, right? And if you think about molecular forces, what are the chemical bonds that hold molecular substances together? And that is covalent, which I almost just said, and polar covalent. So if you break covalent or polar covalent bonds, then you end up with new compounds, and that's a chemical reaction. Notice here, however, I said forces between ions because we have ionic bonds as well, right? Now, if you break bonds between ions, you don't necessarily have a chemical reaction. What happens is, like, for example, it could be that you've melted it, or it could be that you've shattered the crystal and the forces between some of those ions is broken. More specifically, if you break the covalent and polar covalent bonds in a molecule, that's a chemical reaction. Looking at intermolecular forces is often called van der Waals forces, named after the scientists that studied a lot of them. And so whereas intramolecular forces are the forces inside the compounds, intermolecular forces are the forces between separate molecules. So these are not the chemical bonds that keep individual molecules bonded together. Rather, these are the forces between groups of molecules. So these forces hold the molecules together to form a solid or liquid in molecular compounds. Breaking these bonds, or breaking these forces, results in a physical change, such as a change of state. Okay, and the stronger the intermolecular bonds, the stronger the intermolecular bonds, the higher the melting point and boiling point of the substance, right? So if you have very strong intermolecular forces, that would require a lot of energy to break those forces to create a change of state. The types of intermolecular forces that we're going to look at, there's one that's called London dispersion, and another one that's called dipole-dipole, dipole-dipole, and a specific type of dipole-dipole that is called hydrogen bonding. So these are the three types of forces that can be present between separate molecules, and those are your intermolecular forces. In contrast, these are your intramolecular forces, which we have previously studied. And those are the forces between atoms inside the molecule or in the ionic compound. All right, let's talk about these three types of forces, because this is something that you've never seen before, right? You've never seen or encountered London dispersion, and I'll just rewrite that if you can't really read that. That's London dispersion. Okay, let me just erase this. Oops, sorry. London dispersion, and this is dipole-dipole and hydrogen bonding. And you'll see, if you're not sure, they're restated here at the top. So London dispersion forces are forces that exist between all molecules, regardless if they are polar or non-polar. So London dispersion forces will always exist in molecular substances, because molecular substances are the substances that produce molecules, right? Ionic compounds produce crystal lattices. So these London dispersion forces will always be present between molecules. And how they form is that the electrons temporarily shift in one direction. So the electrons in the atoms shift in one direction, and this creates a temporary delta positive, delta negative. Okay, this temporary delta positive, delta negative, okay, or this temporary dipole, di meaning two, poles like positive and negative, on the molecule induces a shift of electrons on a nearby molecule. Now there is an attraction force between the temporary delta negative of one molecule and the delta positive on a nearby molecule. And then that temporary dipole will disappear and the process starts again. Okay, although these dipoles are weak and temporary, the collective effect is significant. So the forces happening between all the molecules of a substance add up to create significant forces. So again, this may seem like a lot of information and it might be difficult to process. So what we're going to do is we're just going to take a look at what's happening here on a with a diagram. So what happens is we have, say for example, a hydrogen atom, and number one says the electrons temporarily shift in one direction in the molecule, which creates a temporary dipole. So if we took a snapshot of the hydrogen molecule, it is possible that the two electrons that it's sharing end up on that side, right? An example of this, or an analogy, would be if you were to take a picture of bees buzzing around a beehive. The bees would not be perfectly distributed around the beehive, or like evenly spaced around the beehive. If you took a snapshot, you would find that you'd find clumps of bees, right, in one section of the hive. And then if you took another snapshot a second later, you'd find the B's in another section of the molecule, right? So it is with electrons. If you took a snapshot in time, the electrons sometimes clump around one edge, right? So that is step one. The electrons temporarily shift to one direction. And if the electrons are temporarily shifted over here, and again, this is temporary because this shift is going to disappear in a second, you have a slight temporary, so this is a temporary delta negative, and this would be a temporary delta positive. Okay, so that's, sorry guys, that's a temporary delta positive. This temporary delta negative, because so now we have like the two electrons over here, because you have negative charges on this side of the molecule, these negative charges will repel the electrons on a nearby molecule. So we're looking at step two now. The temporary dipole on the molecule induces a shift of the electrons on a nearby molecule. So the temporary delta negative here, because those are negative, takes these negative electrons on a separate molecule and pushes them to this side. It repels them. And so over here we have now a delta positive here and a delta negative that has been produced by pushing the electrons over to this side, which was caused by this molecule. Okay, and now what we have is we have an attraction force. This is step three. There is now an attraction between the temporary delta negative of one molecule and the delta positive on the nearby molecule. So now we have a force of attraction between these two molecules. And that force of attraction is what we call our London dispersion force. So although these dipoles are weak and temporary, number four, effectively what happens is that then the temporary dipole disappears and we end up with, the electrons dispersed throughout the molecule. And it basically keeps happening again and again and again and again and again, right? So like in a snapshot in time, they might be now on this side, which will create a temporary delta positive, delta negative that shifts the electrons on a nearby molecule, and you get an attraction force, and it repeats again and again. Trend in the strength of forces. As the number of electrons in a molecule increases, so as we have more electrons in a molecule, the electron clouds, so the shared electrons, become less dense. And that's because as you add more electrons in a molecule, those electrons will each repel each other. So the electrons within a molecule will spread out a little bit more, reducing the density. So with the more spread out electrons, so the less dense electron clouds are now more easily distorted, which causes more temporary dipoles. So if you want to assess the strength of the London dispersion forces, you look at the total number of electrons in an atom or molecule, and if there are a high number of electrons, well, that means that you have less dense electron clouds, and the London dispersion forces will be strong, and you'll have a high melting point or boiling point. All right. Next that we're looking at is dipole-dipole forces. And dipole-dipole forces will only exist between polar molecules. So it has to be a polar molecule. The stronger the London they are stronger than London dispersion forces, because remember that London dispersion forces are temporary, right? They appear and then they disappear. They appear and then they disappear. So they tend to be stronger than London dispersion forces. The only exception would be if the London dispersion forces are extremely strong, and that would mean if there's a very, very high total number of electrons, in which case then your London dispersion forces would be much stronger. If you want to ask about what the breaking point is, what the number of electrons is, there's no really set number. You just have to look at the actual melting points and boiling points of the substances to determine that information, because there are many factors that actually contribute, and like many things in this course, we're trying to simplify this to give you the basics. So how do dipole-dipole forces form? Well, you have a permanent delta positive and delta negative on one molecule. So if we were to take a look at this, these would all be delta negative because the electrons are pulled over to this side of the molecule. And this is delta positive. This is delta negative. And this is delta positive. So because we have unlike slightly different charges here, like delta positive and delta negative, we're going to get an attraction force between these two molecules. And the same thing can be said for over here. We have a delta positive, delta negative over here, and we have a small attraction force between these two ends of the different molecules. Again, remember, these are forces between molecules. They are not the forces inside the molecule, right? If we go back up here, we repeat that these are the forces between separate molecules. Okay, so that we just studied the dipole-dipole, and we also looked at London dispersion. Again, these are all between separate molecules. Hydrogen bonding is a type of dipole-dipole that happens when there's a hydrogen bonded to a very electronegative atom. So the bond itself is not the hydrogen bond. Okay, so I'll explain this in a second. For hydrogen bonding to occur, we have to have the following atoms, nitrogen, oxygen, and fluorine, which are very electronegative, and they have to be bonded to hydrogens. So you can see here, right? The hydrogen has to be directly bonded to the oxygen, fluorine, or nitrogen. So hydrogen bonds are very strong. They're about 1/10 the strength of equivalent bonds. Okay, and here's how they form. The hydrogen bonds, the bonds of H to O, H to F, H to N inside the molecule, and because they are inside the molecule, we would say that those are our intramolecular bonds. Those are very, very polar, and they cause a large shift away from the hydrogens. Since hydrogen has no inner electrons, it has no nuclear shielding, once those electrons shift away from hydrogen, we basically have a positive nucleus, and that's partially exposed when the electrons are shifted away. And then the partially exposed positive nucleus, the delta positive, is strongly attracted to the delta negative of the N, O, or F of a nearby molecule. So again, lots of information. Let's go back and look at how they form again. So step 1 says the hydrogen oxygen, or hydrogen fluorine, or hydrogen nitrogen bonds inside the molecule are very polar. So we'll take a look at water here, right? In the example here, that these right here, this OH bond here is extremely polar. And that means that the electrons will strongly be shifted away from the hydrogen, creating a delta negative over here and a delta positive over here. Okay, this oxygen, because it is very electronegative, really pulls the electrons over to it. Same thing over here. We have the electrons being strongly pulled away from the hydrogen over to the oxygen. And you have delta positive here. Okay. What you end up having is then you have an attraction force between the hydrogen of one molecule to the oxygen of another molecule. And that is an extremely strong attraction because, look at step 2. Since hydrogen has no inner electrons, once these electrons are pulled away from hydrogen, its nucleus is partially exposed, right? Its proton is partially exposed, which creates a very strong delta positive. So this delta positive here on the hydrogen is extremely strong because the electrons have been pulled away from it towards the oxygen quite strongly, enough to expose this nucleus. And so this partially exposed nucleus, which is very positive, becomes strongly attracted to the delta negative. And so to be very clear, this green dotted line here, that is the hydrogen bond. Inside the molecule here is not the hydrogen bond. Okay, so this strong attraction between the oxygen and the hydrogen of separate molecules is the hydrogen bond. The force of attraction between the oxygen and hydrogen inside the molecule, well, that's just a polar covalent bond. That is not the hydrogen bond. That's a key distinction that I want to stress because that is often a point of misunderstanding for students in the course. They often think that the hydrogen bond is inside the molecule when it is in fact the bond outside between the molecules, right? Because hydrogen bonds, and we'll scroll back up to the top again, going back to here, hydrogen bonds are the intermolecular forces. They are the forces between separate molecules. So if we look down over here, we have 3 substances and 3 boiling points. Okay, these boiling points are given in the Kelvin scale. So that's just a different temperature scale that we often use for other temperatures. If I was to take those temperatures, which are in Kelvin, which is a different temperature scale, like Fahrenheit, it's a different temperature scale, I'm just going to give you them in degrees Celsius, and that's 36 degrees Celsius. So this compound boils at 36 degrees Celsius. This compound over here boils at 47 degrees Celsius. And this compound over here boils at 118 degrees Celsius. So what are the types of bonding between molecules? Well, since C5H12 is non-polar, so the molecule itself is non-polar. Because the molecule itself is non-polar, we can't have dipole-dipole forces because dipole-dipole forces only exist between polar molecules. And if we don't have dipole-dipole forces, we certainly don't have hydrogen bonding. So the only forces that exist between these molecules are London dispersion forces, because London dispersion forces exist between all molecules. So the only forces that are present here are London dispersion forces. And we can determine the strength of the London dispersion force by counting up the total number of electrons. Not just the valence electrons, but the total number of electrons. So we have carbon, there's 5 carbons, each with 6 electrons, plus 12 hydrogens, each with 1 electron, for a total strength of 42 electrons. So that is your London dispersion strength. Okay, there's 42 electrons present in that molecule, so that gives you a sense of the degree of strength of the London dispersion forces. If you look at the next molecule, the next molecule is polar, C3H7Cl. It has to be polar because effectively what you end up having is 3 carbons bonded together. Okay, there's a bunch of hydrogens, but then there's a chlorine attached to the carbon there, and the carbon to chlorine bond is polar, creating this delta negative over here and your delta positive over here. So this is a polar molecule. It's a polar molecule, and effectively what you end up having is you end up having both London dispersion forces and dipole-dipole forces. So you have 2 types of forces now acting between these molecules. And because you have 2 forces acting between these molecules, the boiling point is higher. It takes more energy to separate these molecules from each other. And if you were to count up the London dispersion forces, you would have 42 electrons. So it has the same strength of London dispersion forces as the previous compound, but it has a higher boiling point because we have these dipole-dipole forces of attraction between the delta negative of one molecule and the delta positive of another. So we have another type of force between molecules. The next is C4H9OH, and because we have an OH bond inside the molecule, that will produce hydrogen bonds between separate molecules. Okay, and because we have hydrogen bonds between separate molecules, we are going to get then hydrogen bonding. We will also have London dispersion forces because, again, if you scroll up to the top, it says here that London dispersion forces exist between all molecules. If you were to count up the strength of the London dispersion force, it's 42 electrons. So this has the same strength of London dispersion as all three of these other substances, but it also has hydrogen bonds, which means that it's got another stronger force of bonding between the molecules, which produces a much higher boiling point because it takes more energy to separate these molecules from each other. So just to recap, we started the lesson by looking at the types of bonds. We looked at intramolecular. These are the chemical forces that hold molecules together. Okay. This is something that we've studied previously. Then we looked at intermolecular forces, and these are forces between molecules of a compound, and that's the forces that keep the molecules together in the solid or liquid state. We looked at London dispersion forces, which is the production of temporary delta positives and delta negatives caused by a random shift in the electrons. And those London dispersion forces are always present. So regardless if the molecule is polar or nonpolar, they're always present. Okay. Dipole-dipole forces exist between polar molecules. So you look, if the molecule is polar, it will have dipole-dipole forces. And those are slightly stronger than London dispersion forces. However, it's important to always calculate the total number of electrons in London dispersion forces because it will help see how strong those London dispersion forces really are. And then finally, we looked at hydrogen bonding, which is a special type of dipole-dipole forces between molecules that have these types of bonds, the HO, HF, and HN bonds. Okay, thanks for watching.